Okay, welcome to the Notice of Termination training sponsored by the College of Stormwater and the State Water Resources Control Board's Training Academy. I'm Eric Burnson, formerly of the State Water Board, now with the Kalispell Natural Resources Department up in Northeast Washington. Really happy to be able to deliver this training for folks today. We're going to focus in on two elements of terminating the project in the construction general permit. We're going to first focus on final stabilization or demonstrating final stabilization using the Russell II computer model. And then we'll also talk about post-construction runoff reduction as calculated in the state's automated reporting tracking system, or SMARTS. And so it's sort of a two-part module. So we'll start off with Russell II. First, wanted to give you guys some context on how the Russell II method fits within the notice of termination requirements in the permit. So one of the NOT requirements is demonstrating final condition. So it's a subsection of this 2D here, section 2D1A in the permit. And in addition to photo documentation, the board actually requires that you demonstrate site stabilization using one of three different methods. So the first one is the 70% final cover method. So this is a method that's been in previous iterations of the general permit. And it basically says that you have to demonstrate that you have at least 70% vegetative cover on your project in the post-construction condition. So you need pictures for this, but there's no computational proof required for this. The Russell II method, which we'll talk about at length in this training, it is basically a computational exercise, and the standard is essentially showing that the sediment delivery in the post-construction condition is the same or less than what you have in pre-condition. So we'll spend a good deal of time on how you would demonstrate that in Russell II. The third method to demonstrate site stabilization is the custom method. I think the easiest way to explain that is with an example. Let's say you have a project that's got a long-term monitoring record pre-construction for, say, suspended sediment concentration and turbidity. You could actually demonstrate that a site is stabilized by monitoring that project post-construction and showing that those turbidity levels or sediment levels, suspended sediment concentration levels, were equal or less than what's under pre-construction conditions. So that's another method that the Water Board allows dischargers to use. But we'll focus mostly on the Russell II method under this item B here. So next slide here, Russell II. Russell stands for the Revised Universal Soil Loss Equation. And so this is a method that's been around for quite some time. It actually, the original model was called the Universal Soil Loss Equation, came around in the late 70s. It had its origins in agriculture, so there was a real interest in predicting erosion from agricultural land uses, and over the years it's been adapted for forestry, it's been adapted for construction type applications. So Russell II is what we're going to spend the remaining part of this section on discussing. It's not to be confused with Russell. Russell is actually the sort of the hand calculations, and those sort of form the basis of Russell II. Russell II is the computer program. And the one thing about Russell II, it actually computes sediment yield as well. So just in sort of simple terms, sediment yield differs from soil loss and erosion in that it accounts for deposition on the landscape. And so it looks at erosion, but it also looks at the deposition of sediment on the construction site. And that ends up being the standard that the Water Board holds you to is really sediment yield coming off the site. The sediment yield in the post-construction condition has to be equal or less than what happens in the pre-construction condition. And so back a few years ago, Caltrans actually developed a California version of the Russell II model. Russell II was developed by the U.S. Department of Agriculture, specifically the Agricultural Research Service. And there's sort of a national version of the model, but Caltrans developed a more California-specific model a few years back, which is really it's really the appropriate version to use for the California construction permit because it has good, up-to-date California climate data, and it also has the erosion sediment controls and management practices keyed to those that you see in the CASCA BMP portal. And so that's, it's a lot more applicable to what we do here in California. The one caution about using Russell 2, it estimates erosion and sediment yield from sheet and rill erosion. That's a really important point and distinction to make. It doesn't estimate gully erosion, which may be the dominant erosion process on a particular site, especially if we're looking at, say, pre-construction conditions on a previously grazed site, or some other type of site that's got other types of erosion going on. It doesn't look at mass movement or landslides. It doesn't estimate channel erosion. It specifically estimates sheet and rill erosion. So that doesn't end up being a real liability, because that sheet and rill erosion generally is the dominant erosion process on construction sites. So that's why we're fairly comfortable deferring to that method for estimating erosion and sediment yield off of construction sites. So Russell 2 basically uses a sort of a conservation of mass to estimate rill and inter-rill erosion. Inter-rill is another word for sheet erosion, so there's a lot of, once you start looking in depth into the model and all the erosion literature, you'll see these terms used interchangeably. So sheet erosion and inter-rill erosion are the same thing. And likewise, erosion and soil loss are also synonymous. So just to keep those terms in mind here. So what Russell 2 estimates is soil loss and sediment yield from sheet and rill erosion, or rill and inter-rill erosion. And so Russell 2 is available from the Caltrans website. Caltrans has dedicated a specific website to Russell 2. So this is sort of the California version of the national Russell 2 model. And so here's the URL here. You guys can download it, and there's a lot of really good documentation on this, and we'll point to that throughout the training here today. There's a lot of really good documentation and helpful guidance materials on here, as well as the model and all the data sets. So that's probably the first step if you're going to use Russell 2 to demonstrate site stabilization for the construction permit. This is the version that is recommended to use. So Russell 2, basically, here's just a screenshot from the first interface that you'll see when you open up Russell 2. It models everything as kind of layers. Okay, so there's key tabs within a Russell 2 project. You're basically asked to open up a project file, and so it models everything as sort of a layer here. So there's some key tabs within Russell 2 that we'll discuss in a little bit more detail throughout the training today. One is the soil tab, so looking at your soil quality and actually soil parameters, specifically texture, and basically the type of soil you have, because that has a huge influence on how erodible that soil is. There's also a tab on management measures, and so Russell 2 has its origins in agriculture. Like I said, Universal Soil Loss Equation, Russell 2, they all really started with predicting erosion and sediment yield from agricultural land uses. So there's this sort of legacy. These terms cover in practice really have their origins in ag, but I think the easiest way to think about it in a construction permit sense and construction application is cover really refers to your erosion control measures that you're going to use. Things like vegetation, mulch, erosion control blankets, things that you're going to put on the soil to actually keep it from being detached. And under the practice part of the management tab, that's getting at more of your sediment control BMPs, like your straw rolls and barriers and sill fence and that sort of thing. Sediment controls are practices that you're using to trap sediment that's already been dislodged. So sed basins is another good example of a sediment control. These can all be modeled within Russell. The other tab is a topography tab, so that's looking at things like how steep is the slope, what's your slope length, and so that actually has a huge influence on how much erosion is happening on your site. And there's also this barrier placement tool, permeable barrier placement tool within Russell, so you can look at the placement of different types of barriers to see how that affects the erosion and the sediment delivery off the site as well. So we'll go through all these tabs in a little more detail. So just to give you an overview of the equation, sort of the background equation in Russell 2, there's 5 parameters in Russell and Russell 2. So the way I was always taught to remember it is Rickle-Skip, whatever mnemonic you want to use, but Rickle-Skip seems to work in my head, but however you want to remember it. But it's really just 5 factors that are used to predict soil loss and sediment delivery coming off a site. So rainfall runoff erosivity factor is basically the easiest way to think about that is it's sort of an energy term. It gets at what kind of energy is available from the rain and the runoff to dislodge sediment. So that's sort of your climate factor in Russell 2. Soil erodibility, it's the K factor, and so that's very much tied to the soil texture. It's also tied to things like the percent organic matter, what the soil structure is. We'll go into a specific example on how all those things work together to determine how erodible the soil is, and that's just soil erodibility is really a measure of how readily that soil detaches. Slope length factor is getting at the horizontal length of the slope, so the longer the horizontal slope length, generally the more erosion you have. Slope steepness usually expressed as percent slope. The steeper the slope, the more erosion you're going to have. And then the cover factor, again, that's in Russell 2, that's used to simulate erosion control practices like mulch and vegetation. And then the P factor, which is the support practice factor, and that's used to simulate the sediment control practices. So those 5 factors work together to get at what the erosion and sediment yield is coming off the site. So an increase or decrease in any of those factors is going to give you a resulting increase or decrease in erosion and sediment yield. So here is the first screenshot that I wanted to show you, and this kind of shows all those different 5 factors in Russell 2. So just in order, Rickle skip or whatever mnemonic works for you. But the R factor you'll see in that pull down box, that's very much tied to location. So location, location, location. You know, applies to selling a house, applies to Russell. It's all about where you are in the world. That's going to determine what the climate is and what R factor you're going to use. So we'll go into more detail on how you gather the data to determine what the appropriate R factor is. The K factor, that's tied to the soil. There's a soil tab. You guys see that towards the bottom of the screen here. So there's an option for inputting a site-specific K factor. You can either go into the soil survey data, which I'll talk about in a minute, or you get a site-specific K factor if you have a specific soil data available. The LS factor, so slope length, in this case 50 feet, just for kicks, that's our example here, 50 feet slope length. We've got a slope steepness of 25%. And then the C and the P, so under the management factor, that's where you're going to find C. There's actually some P factor inputs under the management tab, and then the permeable barrier placement tool. So that gives you the ability of putting barriers along the landscape and simulating the P there. And so I'll point out up in the upper right hand corner here is your estimates of soil loss. Again, soil loss being synonymous with erosion. And the units here are basically tons, and then sediment delivery, which includes accounts for the amount that's actually deposited on the landscape. What Russell 2 does is give you sort of a real-time accounting of your estimated soil loss and sediment delivery is. So you can go in and change any of these factors, and it'll actually give you sort of a real-time output of what your soil loss is and sediment delivery is. So with these factors that we have in here, this is basically 22.4 tons per acre. So let's go through each of the inputs in a little bit more detail. So the first factor, the R factor, I kind of showed you on the previous slide where that's located. We're going to go into a little more detail on where you would find the information to be able to input the data to get the R factor. So probably the best source of information to use is the NRCS Electronic Field Office Tech Guide. NRCS stands for Natural Resources Conservation Service. They're basically an agency within the U.S. Department of Agriculture. Forest Service is another example of USDA agency. So they're basically charged with private land conservation. So there's a lot of really good references that NRCS has put out, a lot of good Russell 2 guidance, a lot of soil loss and erosion prediction software, materials, that sort of thing. They also author some of the runoff prediction methods that we use with hydrology and drainage design. So in this particular example, just looking at Lancaster down in Southern California, you basically go to the Electronic Field Office Tech Guide, And there's a file, there's actually within the Field Office Tech Guide, there is a specific link to Russell 2 parameters. And so I'll show you this next slide here. This is showing the data that comes from this particular Field Office Tech Guide that applies to the service area covered by the Lancaster Service Center down in LA County, and it incorporates LA County and Orange County. And this map is basically showing polygons with annual precipitation ranges. And so it turns out that R factor is very much tied to the amount of annual precipitation you have in a particular area. So that the first step in determining the R factor for your project is determining what precipitation range you have. And so for this particular case, we've got these different breakdowns of precipitation ranges. This could certainly, you can see these numbers, you can imagine these numbers changing considerably if we go up to, say, North Coast, Humboldt County. So these are going to vary depending on where you are, but in Lancaster these are sort of the precipitation breakdowns. This is a really critical piece of information that's used to determine what the R factor is. So if you know what precipitation sort of polygon you're within, then you can determine what your R factor is. Okay, so the next factor is the K factor, and so that's the soil erodibility factor. So there's two different methods to determine K factor in Russell 2. One is using web soil survey data, and so we'll go into that method in a little bit of detail. So the soil surveys have now been pretty much digitized, and I'll show you the link to get that information. The other source of information for K factor can come from a soil report, or specifically a soils component of a geotechnical report. So we'll go through those two methods in a little bit more detail. So here's the link to the web soil survey. So the URL is up in the upper left-hand corner there, and so it's pretty straightforward. There's a lot of really good information on this site. It's pretty intuitive. I mean, you just hit the big green start button, and that's how you basically get into the program. So one of the first things they're going to ask you in the web soil survey is defining what's called your area of interest, and that's what AOI stands for. These top two buttons, you'll see that the arrow is pointing to one of the AOI buttons there, but essentially it's asking you to define your area of interest. So in this case, in Orange County, we've basically traced out this triangle that gets at what this area of interest is. So that's the first step, is defining what your area of interest is. And there's actually a sort of a cutoff. You can't have too large an area, otherwise it's going to give you an error message saying you've selected too large an area, and I think it's about 10,000 acres or something like that. So you have to, it might be an iterative thing where you're trying to, you might go too big the first time, but you have to sort of scale it down to an appropriate size. But this is our particular area of interest, just for example. And then it's actually going to generate a soil map for your particular area of interest. And so what this is showing is the different soils that are mapped in this area of interest. And so I'll just point you guys to the soil properties and qualities. All this is under Soil Data Explorer. So that's going to give you, once you have your soil map here, Soil Data Explorer is going to give you all this data on what type, basically on the relevant soils in your area of interest. So we're specifically interested in K factor in whole soil. It's going to give you a couple different options for K factor. One is for whole soil, the other one is rock free. You want to actually use the whole soil K factor, because what that does is that's going to incorporate rock fragments, it's going to incorporate organic matter. Those are actually things that keep the soil from readily detaching. So you want to actually use the whole soil K factor as opposed to just the rock free. So there's a couple different selections again, but that's the whole soil K factor is what you want to use for this Russell 2 output. And so once you determine the map soils, if you hit that View Rating tab, this is what it's going to give you. It's going to give you the map unit name, and it's also going to give you the K factor that's associated with each of those map units. So in this example, we have three different types of soils. We've got this Metz loamy sand, we've got this San Emigdio fine sandy loam, and then we've got another sort of map unit of the same San Emilio fine sandy loam, but it's got a moderately fine substratum. So they make that distinction, but it actually has the same K factor as the other fine sandy loam here. So there's two different K factors. This tab also has some pretty good explanatory text on what the ranges of K are. They generally range from just over 0, about 0.02, up to about 0.69. And it's very much tied to soil texture. So you generally have those higher K factors for soils that have a lot of silt and fine sand in them. So we would expect soils that are dominated by fine sand and silt to have K factors, on the range of 0.5, 0.6 or so. So here we have, in this particular example, we've got K factors of 0.2 to 0.32. So to sort of put this into practice, what you would do is you would you'd look at the area of the site that's actually represented by these certain K factors and do sort of a weighted average. So if we have 9.5 acres of this 13.5 in the example of 0.2, we'd sort of aerially weight that. So 9.5 out of the 13.5 is 0.2, and then the rest of it is 0.32. We'd have sort of a weighted average K factor, and that's something that you can manually enter into the Russell II model under that soil tab. So that's kind of the first method. That's a sort of a brief overview of the web soil survey, but that's a good way to go if you don't have any site-specific information. What's really preferable is really getting more site-specific information. So I'll go through how to do that. We're calling that the soil analysis method for the training here, and there's really just a few pieces of information that you need to come up with a site-specific K factor. So the first one is texture, and texture is basically the percentage of sand, silt, and clay particles in a soil. That's really all it is. And so we can derive that by doing sort of a sieve analysis. And so if we go through and we figure out how much percentage of the soil passes a certain size sieve, we can get basically a percentage of sand, silt, and clay from our sample. Permeability is actually a lab test as well, so that's something we can come up with a permeability class, inches of water per hour, and sort of put it into a different permeability class, so that's a standard lab test as well. And then soil structure is something that, so texture is the percentage of sand, silt, and clay. Soil structure is how those sand, silt, and clay particles are arranged. Okay, so there's texture and structure. Those are really the two primary soil quality variables that we're interested in deriving a K. So this table kind of shows the relationship between soil texture and structure and permeability. So sort of in summary, if we have on the left-hand column here, we've got clay, silt, sand, texture, soil. Clay texture soil tends to be, or soil that's dominated by clay particles, tends to have a fine granular structure. And I'll show you a slide. The next slide has sort of examples of what these different soil structure types look like. But very fine granular structure, and that in turn leads to very slow permeability. Permeability is just looking at how readily that water gets transported through the soil profile. Silt generally has fine granular structure to coarse granular structure, and that's sort of in the mid-range of permeability. And then so sand is definitely your most rapid permeability type soil, and the structure is more of a coarse granular, and it can tend to be blocky, platy, or kind of massive structure. So this picture kind of illustrates what structure looks like. Again, structure is the arrangement of these different soil particles, and so you've got granular structure on the upper left, blocky, columnar, prismatic, and platy structure. So those are all things that you need to sort of put the soil into some kind of structural class to be able to come up with a K factor. So what this is all going to lead to is we're going to get into a nomograph in the next couple slides that basically puts all these different factors together. But let's say we have a soil sample from our site, and sometimes, you know, this is where we can use the web soil survey or some other information to determine what types of soils are mapped on the site, and you can actually follow up with more site-specific information, and you might have to do a number of different soil analysis if you have different types of soils. But let's say we have a site with this particular soil type on there, and we've got 65% silt, we've got about 5% sand. Organic matter, we can get at organic matter in terms of a lab test. We can basically burn the soil off and figure out, there's a standard lab procedure to figure out how much organic material is available in the soil. Organic material is the relationship between that and K factor is the more organic matter you have, generally the lower the K factor. In other words, organic matter serves to it serves as kind of a glue to stick those soil particles together. So the more organic matter you have, it's actually going to hold that soil together better and actually cause it to be less readily detached. And so that's kind of a broad, connection there. But that's sort of how organic matter, the relationship between that and soil erodibility. This particular example, we're saying it's got fine granular structure, and then based on our soil test, we have slow to moderate permeability. So we have 5 factors here. When we go through the soil nomograph exercise in a second, you'll see, keep this K factor estimate in mind here, how we arrive at this 0.31. I'll show you how we get there. So this soil nomograph, this actually comes out of the Russell, the Ag Handbook. Here's the reference up here on the top. It's basically a technical handbook, part 618. The URL is up on the top left of this slide. But this is the nomograph that's probably used most often out there in terms of getting a K factor from a specific soil analysis. So just walking through this step by step, based on a sieve analysis, 65% silt in this example. We basically cross that over 5% sand. We have a 3% organic matter estimate, so that's how we get at that intersection there. We basically go over to this right-hand nomograph based on the soil structure, fine granular, which is basically number 2 here. We basically intersect that number 2 line, and then based on our lab test, we have a permeability slow to moderate, and basically coming across, and this is our final answer here. K factor equals 0.31. And so, yeah, you can basically fool around with different combinations of silt and sand and organic matter and arrive at all different types of estimates for K factor. But this is sort of an overview of how you would get at a K factor based on lab data. So it's pretty straightforward. And you can see the ranges we talked about 0 up to about 0.69, 0.7. So that's how we arrive at that. So this is really the preferable way to go, I would say, is using site-specific information to come up with a K versus the web soil survey. But sometimes, it depends on the project, but sometimes you only have enough resources to just do web soil survey. But it's always preferable to use site-specific data to come up with a K factor. So the next 2 factors are really the topographic factors in Russell 2. And so specifically it's slope length, and it's the horizontal slope length, and we have a graphic in here that kind of shows what we mean by horizontal slope length. And then slope steepness is the other topographic term, so that's in percent. So in this example we've got 25% slope steepness and 50-foot slope length. And this is where the site designer has a lot of flexibility in this. In many cases, these factors are going to change between pre-construction and post-construction. Certainly, if we're doing cut slope or fill slope and modifying the landscape, these numbers are going to change. So this graphic shows what we mean by horizontal slope length. So instead of the length from the top of the slope to the point at which you have deposition, it's that horizontal slope length. So in reality, I'll tell you that it's kind of difficult to deal or determine this parameter in the field. But Russell 2 isn't super sensitive to slope length, fortunately. But once you get practice, you get out in the field, you can sort of determine what this horizontal slope length is. What you're doing in practice is looking for clues out there on the landscape, top of the slope versus evidence of where soil starts depositing. Once you get a little bit of practice doing this, you can get a pretty accurate number for what that horizontal slope length is. But that's the slope length. That's the length term that Russell requires. It's not the length from the top of the slope, sort of down the slope to the point at which it deposits. It's that horizontal slope length. So the next Russell 2 factor is the C factor. So again, we talked about that being things that we are actually covering the soil. So in this particular screen, we've got an existing condition. So we've got Russell 2 breaks down the different vegetative cover, existing vegetative cover in terms of the type, grass and forbs, mixed grass and shrubs, and then percent cover. So percent cover also takes some practice determining, and the Caltrans has some good documentation on this in the Erosion Protection Procedure Manual. This is where site photos are really invaluable for coming up with percent cover. So this is right out of the guidance manual the Caltrans produced. This is looking at different percent covers. I mean, the whole idea with this is sort of breaking the site down into 4 different quadrants and imagining the different vegetation sort of pushed into a corner. So that's what this is all kind of getting at. So this takes some practice too, but once you go sort of calibrate your eyes and sort of how you're looking at this, you can come up with pretty accurate estimates of what the vegetative cover is. So this, in conjunction with site photos, you can get a pretty good estimate of what the percent cover is. And like that screen showed you before on Russell 2, it's very much the C factor that you get is very much tied to the percent cover. Basically, the more percent cover you have, the lower the C factor, which kind of makes sense when you think about it. You're going to have less erosion when a project is well covered with vegetation. So again, site photos are really important for C factor, helping with determining what the factor is. So just for assisting you guys on how to sort of look at what different percentages look like, this is an example down in Southern California that shows 20%. So there's quite a bit of bare ground here, but there's also a little bit of vegetation. Some of it can be scattered too, so it's it's getting familiar with kind of in your mind pushing all this vegetation into one corner and coming up with a percentage. So 20% for this one, give or take. 50%. Here's an example of 90%, and then 95%. So even 95%, there's a little bit of bare ground. For the most part, this is a pretty well vegetated slope. So the final Russell factor is the P factor. So this is basically your sediment controls, and this screen shows the permeable barrier placement tool tab. Sorry, that's a mouthful. So what this allows you to do, in Russell 2, you can place different barriers. In this case, we have a fiber roll that's 24-inch diameter. You can place that at different stages of this, or basically different sections of the slope. And what that's going to do is, again, we talked about Russell 2 giving you sort of these real-time estimates of soil loss and sediment delivery. You can sort of vary where you place these different barriers along the slope, and that's going to give you different estimates of soil loss and sediment delivery. There's also the ability to put sediment basin configurations and design criteria under the management tab, but this is where we're getting at more of these sediment controls. Again, sediment controls are measures that are going to capture sediment as it's dislodged. And so, if we're going to, one thing the regional boards I think look out for, if you place complete reliance on sediment controls, that's probably not the best strategy in the world. I think most of the regional boards are looking for good erosion controls to be in place before they're going to sign off on a project. So, the P factor is something in many cases we're going to want to use to basically minimize the sediment delivery off-site, but placing complete reliance on that P factor is kind of risky business. So just a caution to place out there. This last slide here is sort of a summary, and this is right out of a sort of just a quick Caltrans example, but this is showing sort of 3 different phases of construction. And you'll see we've got pre-construction here. Existing grass and forbs is the cover type, 35 to 70% cover, so there's an associated C factor with that vegetative cover. The pre-construction sediment delivery estimate, and this is really what the number that the regional boards are going to look at, is that sediment delivery number. So is sediment delivery under the post-construction condition less than or equal to pre-construction? So in this case it is. So this is actually a compliant project. This is something that could submit for termination, or actually make the case that it's fully stabilized, and supplementing that with photos. This is something that the project proponent could submit for demonstrating that they meet the final stabilization criteria. But just a couple more words on this slide. You see 1.76 is the estimate for sediment delivery in terms of tons per acre per year. This is also showing the construction phase as well, which, I mean, this kind of shows the utility of using Russell 2, just going beyond just a compliance demonstration tool. You can actually use Russell 2 to figure out what your sediment delivery is during construction. So there's some real real life implications for this. If you know that you're going to sort of jack up your sediment delivery in order of magnitude during construction, that might point you to using different BMPs, or doing different timing of opening up that project, so on and so forth. So you can actually game different types of scenarios and figure out how much sediment is coming off that site during construction. But in the section that deals with final stabilization, the permit, this is really the number that matters, is demonstrating that the sediment delivery post-construction is equal or less than what you have pre-construction. So again, in this case, we have a project that could submit for termination and show that it satisfied the final stabilization criteria. So that's it for Russell 2. That was kind of a broad overview. There's certainly a lot of really good training out there on Russell 2. Caltrans on occasion will put out some training. The International Erosion Control Association at their annual conference will do 1- and 2-day trainings by the actual developers of the model. Will go over in more detail Russell 2. But this kind of gives you an idea of how Russell 2 can be used to satisfy the final stabilization criteria in the construction permit. So our next section, we're going to talk about post-construction calculations within SMARTS.
To learn more about California's water issues and the state and regional water quality control boards, go to youtube.com and check out other videos created by Board Web Support.